In this video we're going to look at cumulative distribution functions. Now this definition that we're going to give here and the properties are true for any type of distribution or any type of random variable, and later we're going to look at the distribution functions or cumulative distribution functions for discrete random variables. Alright, so let's look at the definition. The definition is we'll use a capital F for what we call the cumulative distribution function. And by definition, it's equal to the probability that our random variable x will be less than or equal to whatever the value of that lowercase x is. So it's just the probability that that random variable will be some number less than that little x. Now let's look at some of the properties of this distribution or cumulative distribution function. Since it's a probability, we know that that value will be somewhere between 0 and 1. And x, the value of x, can be any real number between minus infinity and infinity. Now let's look at the second property, and we'll kind of reason if these are true or not. Alright, so our function f of minus infinity, let's see, what would that definition be, or what would that be equal to? It'd be the probability that our random variable would be some number less than or equal to minus infinity. Well, obviously the way that we've defined minus infinity, that can't ever be possible. So therefore that probability of that occurring has to be equal to 0. Now looking at f of infinity, we see that that would mean that what's the probability of our random variable x being any number less than infinity? Well, obviously, if we're dealing with, practical things, that has to be always possible, always true, and therefore the probability of that occurring will be equal to 1. It's the always be possible, or will be always true. Therefore, probability is equal to 1. Now the function. Let's suppose we have two real numbers, x1 and x2, where x1 is less than x2. If that's true, then the cumulative distribution function at x1 will always be less than, or it could be equal to, the value at x2. So what does this mean? That means that this function, as we move from left to right, or as our numbers continue to increase, that this function will keep getting bigger. It'll either stay the same or keep getting bigger. It'll never get smaller. So it's a continuously increasing function. Alright, the last property is that what's the probability of our random variable being between two numbers, x1 and x2? Now, here we see that we have a less than sign here and a less than or equal to sign here. It has to be this way, the way that we've defined our function up above. We're not going to get into that here for this course that I'm doing this video for. We won't ever have to worry about what happens exactly on those points and so forth. But note that by definition we really need to be talking about a less than sign here and a less than or equal to sign here. But what the probability of our random variable being between those two numbers will just be equal to f evaluated at the larger number minus f at the smaller number. And that'll be the probability that it'll be between those two numbers. Alright, so given that, if we look at the probability that x will be greater than some number, that we can redefine that or show that as the probability that x will be between whatever that number is and infinity. So using the above property, we can say that that's equal to f of infinity minus f at whatever that x1 value is. And we know that from the property 2 that f of infinity is equal to 1, and therefore this will just be equal to the 1 minus the cumulative distribution function at that x1 value. So now let's look at what the cumulative distribution function is for a discrete random variable. And in this case we'll look at a finite discrete random variable. So for a finite discrete random variable we have an example here where we have the range values going from x1, x2, x3, all the way to xn, finite number of possibilities. And suppose we know what our probability distribution function is, little f of x. So we know the values at f of x1, f of x2, and so on. Then our cumulative distribution function at any value x, let's say we have some value little x, that value of the function will be equal to the sum of all of the distribution values, our probability distribution values, where the value that we're looking at, little x, is greater than or equal to the value of the range value, f of x sub I. So if these were all in order, and let's say that the value of x was, let's say, between these two, between x2 and x3, then we would sum up all of the f values below that. It would be the sum of f of x1 plus f of x2. Alright, that's a lot to put together. Let's take a look at an example now and see if we can show what we mean by all those for a discrete random variable. Alright, so we're given a probability distribution function for this random variable x, and so that's what we're given here. These are the x values, 1, 2, 4, and 6, and we know the distribution at each of those, 0.2, 0.5, 0.1, and 0.2. Okay, so that's what we need for our discrete random variable and its probability distribution function. Now the question is to find the cumulative distribution function, that's our capital F of x, and find the probability that our random variable will be less than or equal to 4.5, will be the probability it'll be greater than 4.5, and the probability that it'll be between 1.5 and 4.5. Okay, so I just wrote down, remember, our definition of our cumulative distribution function, capital F of x, is the probability that our random variable x will be less than or equal to whatever that little x value is. Alright, now let's look at just a couple examples of the function. Now, and I've kind of got them grouped in here a little too close. I probably should have written a separation here, but let's suppose our little x is 1.5. Then let's find capital F of 1.5, or our cumulative distribution function at 1.5. By definition, that'll be equal to the probability that our random variable will be less than or equal to 1.5. So that means, looking over here, that 1.5 value is in between 1 and 2. So what's the probability that our random variable will be less than that 1.5? Well, the only possibilities that are less than 1.5 for our random variable is 1. So that means that we're really asking, what's the probability that our random variable will be equal to 1? And so that will be equal to 0.2. So probability that our random variable will be less than or equal to 1.5 is the same as the probability that x will be equal to 1, and that's 0.2. Now let's look at another example in here. Suppose x is 2.1. So f of 2.1 will be the probability that our random variable will be less than or equal to 2.1. 2.1 is above this 2 and below 4, so it's in here somewhere. So that means that what's the probability that our random variable will be less than 2.1, less than or equal to 2.1, means that essentially the possible outcomes would be 1 and 2 for this RV, and therefore the probability of it being 1 or 2 will be the addition of those two probabilities. So the probability of it being less than 2.1, less than or equal to 2.1, will be the probability it will be equal to 1 plus the probability it will be equal to 2. Or if we add those up, we get 0.7. Now let's look at, I drew our function down here, f of x, capital F of x, and I drew it as a function of that little x. So I put our values 1, 2, 3, 4, 5, 6, 7, 8 here. And let's take a look then for our function. Let's suppose we're right here around 0.5. What's the probability our function will be or our random variable will be less than 0.5, less than or equal to 0.5. Well, obviously that can't happen with this RV, so that probability will be equal to 0. Now notice that I've drawn an open circle here at 1, and it's kind of hard to see, but a closed circle here at 1 at the upper level, 0.2. Why did I do that? Well, it's because we have the definition is less than or equal to x. Capital X is less than or equal to little x. So let's suppose we were right at 1. Then the function at 1 will be equal to the probability that x will be less than or equal to 1. And that probability will be 0.2, because it's possible that we would get exactly equal to 1, and that probability will be 0.2. So it's a discontinuous function for our discrete random variables. So it's not equal to 0.2 at 1. It's not equal to 0 at 1. It's equal to 0.2 at 1. And it'll be equal to 0.2 until we get to the next value, which is 2. So right at 2, it jumps up to 0.7. I should have written it in here, but notice that that difference here is the value at 2, which is 0.5. So it jumps up by 0.5 to get us to 0.7 at that 2. Now it'll stay at 0.7 until we get to 4, which is the next value, and it'll jump up by whatever this value is at 4, which is 0.1. So it'll go from 0.7 to 0.8. It'll stay at 0.8 until we get to the next value, which is 6, and it'll jump up by 0.2, and that value will give us 1. Now from this point on all the way to infinity, it'll be equal to 1. Now it has to be equal to 1 at infinity based on our properties, so notice that it does not go back down. So if you're drawing this function, it has to stay at 0.1 or approach 0.1 as x goes to infinity. And so it'll stay at 1 all the way out to infinity, and it'll also be 0 down this way all the way to negative infinity. Alright, so now that we have the function drawn, we can use it to find some of the probabilities. So what's the probability that x will be less than or equal to 4.5? By definition, that'll be equal to our function evaluated at 4.5. And so if we look at 4.5, it's right in here somewhere, and that value is 0.8. So the probability that x will be less than or equal to 4.5 will be 0.8. And that is, of course, the addition of those three numbers, 1, 2, and 4. Now the probability that it'll be greater than 4.5, as we found before, is equal to 1 minus the probability that it will be less than or equal to 4.5. We already found that one up above, and so it's 1 minus 0.8, which is 0.2. Now the last one that we were trying to find is the probability that x will be between 1.5 and 4.5. And based on our properties that we had, this will be equal to f at 4.5 minus capital F at 1.5. And if we look at those values, we have 0.8 and 0.2, so the probability will be 0.6. And for our discrete random variables, these are kind of easy to find, these probabilities. We would look at 1.5 and 4.5. 1.5 is somewhere in the middle here, 4.5 is over here, so we sum up everything in between there, which would be these two, which would give us 0.6. So that makes sense. So once you have this cumulative probability distribution function, capital F, you can then use it to find different probabilities.